Okay. Good morning, ladies and gentlemen. All right. Good morning, ladies and gentlemen. Please be grateful to God the Almighty that we can gather together this morning with a very good event on the international webinar on the remote sensing and geospatial information. So today we will see 3 talks. The first one is from S.Si Indonesia, presented by Hafiidh Alfian Affandi from S.Si Indonesia, and then we will also see, we will also watch the talk from Dr. Nurul Hazrina Idris from Universiti Teknologi Malaysia. May I ask Ibu Nurul if she is available right now? Hello, Bu Nurul.
Hello ya Pak, selamat pagi.
Selamat pagi Bu Nurul. Bu Nurul of course can speak Indonesian and Malay. And will join us a little bit later, Professor C.K. Shum from the Ohio State University. So in a very bright day today, we're gonna watch these 3 talks related to the satellite altimetry for monitoring our Earth. First of all, let me introduce myself. I'm Johannes Budi Sulistyo Adi. I'm working in the Center for Geospatial Information Infrastructure Development as part of the Institute for Research and Community Service in the Mulawarman University. So before we start, let's give the floor to the chief of the Institute for Research and Community Service, Pak Anton. Are you there?
Yes, thank you very much, Pak Budi.
All right.
I'm here at the Agricultural Field Station of Mulawarman University.
Right.
Should we start by now?
Yes, Pak Anton. You are free to deliver your opening remarks, and of course also do the opening ceremony before we can start the event. Thank you very much.
Thank you very much for the occasion, Pak Budi. Assalamualaikum warahmatullahi wabarakatuh. Very good morning for everybody who come to the international webinar of remote sensing and geospatial information. And I would like to say a very warm welcome to Mr. Hafiidh Alfian Affandi, Ms. Nurul Hazrina Idris from Malaysia, and also for Professor C.K. Shum from Ohio State University. It is a very honorable moment for us to have such a very good speakers today that will share and deliver the experience on remote sensing and geospatial information. Actually, at the moment, I'm in the middle of the agricultural field. Behind me is the...
Do you mind to turn on the video, Panton?
Yeah?
Would you mind to turn on your video so you can see?
Okay. So behind me is the facility for drying, and we have several other facility behind me. It is about 17 hectares area of field for agriculture testing, including fruits and also horticulture. So this is, and every Saturday we are here to conduct several experiments with students. So without further ado, thank you very much again for coming to the conference, and I hope that the conference will discuss something and will have something very important for the um, science on remote sensing and geospatial information. And once again, for Pak Budi, it is a great honor for you to have such a very good webinar, international exposures in Mulawarman University. So thank you very much, and I think that's all from me. Assalamualaikum warahmatullahi wabarakatuh. Very good morning, and congratulations for the webinar.
Thank you very much, Pak Anton, for the opening remarks and the opening ceremony. So we are now in 9:10, so we are really right on time. Even the participant is still counting up. Now we have 20% in the Zoom and will be growing up in the YouTube as well. So without spending too much time, I will introduce our first speakers, who is Dr. Hafiidh Alfian Affandi. So Hafiidh is the solution engineer from S.Si Indonesia. And today he will talk about the communicating ocean and coastal science through geospatial information. So Mr. Hafiidh, you have about 20 minutes for your talk. If you want to share from your own device, that's okay. But if you also need help, we are also available for help. So without spending too much time, we'll go ahead and please, Mr. Hafiidh, to present the first talk.
Assalamualaikum warahmatullahi wabarakatuh. Thank you, Mr. Budi, for calling me doctor. I hope that will become true. And now I will to present. I will to share about information and our experience in S.Si Indonesia about communicating ocean and coastal science with GIS. First, I want to share my screen. Everyone can see my PowerPoint.
Yes, it's visible clearly, Mr. Hafiidh.
Okay. Is it double or not?
No, it's good.
Okay. I'm sorry. Okay. First, good morning to the audience. I'm very proud and happy to be speaker on this event, and I'm very proud to be able from learn from the speakers, Miss Nurul, Dr. Nurul, and Professor C.K. Shum. And as an opening, I'm here represent S.Si to talk about our technology that can support the maritime and later we will also show you about the examples. On this webinar, I want to tell you about S.Si, about GIS in general, modern GIS as communication platform, and S.Si initiative and conclusion. Our president, Jack Dangerman, is a landscape architect by training and in Harvard University and graduate along with Laura Dangerman and his wife. He founded S.Si in 1969. According to our name, Environmental Science Research Institute, we are a company, research-driven company that spend more than 25% of our annual revenue on research and development, so we can continue to deliver innovative technology that harness the power of applied geography. More than 2,000 users in Indonesia. S.Si is clearly about serving you and our users. That's what we exist for. And my report card to you, we continue to aspire to make difference, not only serving you and through you, but also in greater context by contributing to society to advance GIS and spatial literacy. Our brands in Indonesia, there are 4 brands in Indonesia, in Balikpapan, in Surabaya, and in Riau. We are not only take care of our client in Jakarta, but we try to embrace our users who outside in Java Island to be closer and understand more about GIS technology. SD Indonesia is very care about our users and to be connected in our technology. We are not only focused on our client, on our commercial client, but we also contribute to the next generation to always be connected to our technology. And this is our greatest investment. GIS is not only about map visualization, but is a framework that uses spatial basics, starting from measurement, visualization, and to be able to help us make decisions that can be very useful for the general public. If we want to share our information that has been created and delivered to the general public, this desktop is not sufficient to disseminate information effectively, because this desktop is only on desktop. If we want to share in internet, we need the latest technology, and that is ArcGIS Enterprise and ArcGIS Online. Through the ArcGIS Enterprise and ArcGIS Online, we made the data more accessible, and reliable, as well as easy to access from any device, anywhere and anytime. This we have known for a long time is very familiar with vector data, or we can call it a shape file, 3D file, imagery, and so on. Technological developments encourage GIS technology to be more advanced and able to support all types of data, so that it can perform analysis and geo-enabling data. We can also collaborate with various spatial application providers to make it easier for our users to integrate their data. So far, we are very familiar with printed maps. Print maps have helped us from very long time to assist the development and dissemination of information in Indonesia. But what if we want to display our maps interactively, dynamically, and able to show our analysis process and easily to access from any platform? That is the advantage of map visualization in a browser, or we often known as WebGIS, which is one of the capabilities in our platform in ArcGIS Enterprise and ArcGIS Online. The tools we have developed also make our users easy to perform analysis faster with the help of automation such as geo-artificial intelligence and deep learning. And the process of integrating with various external data sources such as IoT, Internet of Things, or we can call it a sensors, or other kind of data such as big data, multidimensional data is also possible for now. Now the 3D dimension is not only used as a display, but we can use it for analysis and development planning. And then we can also combine it with virtual reality technology, where we can see the original appearance and dimension an object in the real world. Data with quick update would help us work for more efficient in monitoring and preventing unwanted events, not only fast but on a real-time basis. For the example, a ship is sailing in shallow water. As an officer who monitor the situation, we could control and monitor the track of the ship in a real time, and we can provide information if the ship enters a danger zone. That's one of the example of real-time monitoring. Or we can see in this one of this picture that can use uh, real-time technology. We also help field operator to stay connected to the office. The data that has been collected in the field will also be automatically connected to the office and can be used immediately, so we do not need to transform the data. We can use our daily device such as tablet or smartphone. Our field application can also be used in offline situation. If we in the middle of forest or in the middle of the sea, we can stay connected as long as we covered by GPS location. And this is our example, our study case for environmental monitoring. We could see some example for marine studies. Marine studies such as real-time weather and marine marine habitat modeling are very close with modeling data and to predict some situation. And we can escape from remote sensing data for our model, because remote sensing data is very useful for us to analysis, especially in marine analysis. Will help us a lot if we using imagery data. How about Indonesia? The Indonesian government is aware of the importance of spatial data. The management to assist development on land as well as in the coastal zone. From the Ministry of Marine Affairs and Fisheries, or in Indonesia we call it KKP, Kementerian Kelautan dan Perikanan. They collaborate with us, with S.Si Indonesia, to create this application, easy to access and very informative. With this application, we can understand the potential and disaster in each region in Indonesia. We can understand and could help us to carry out the development for planning and economic, social in the region to live harmony with disaster. And the other cool things about our technology is our Indonesian Navy is already use our technology, and they are I'm sorry. Our Indonesian Navy has expert in bathymetric data. The Indonesian Navy has almost reached the entire Indonesian Sea and continues to provide updates for bathymetric data. But some data require special permission to access. But we are able to see that development of JS for visualization and analysis of marine data in Indonesia is very rapidly growing. And this is the other case of geospatial technology. This technology can be used for variety of themes for energy in Ministry of Energy and Mineral Resource, or ESDM, and Bureau of Statistics, or BPS, Badan Statistik, and demographic data. And for the LAPAN, or Antariksa, Lembaga Penerbangan Antariksa Indonesia, already work with us to develop geospatial technology. The last but not least, ESRI also play an active role in disaster mitigation in Indonesia. We are directly participate in the field to help volunteers in disaster mapping. The last event is on Balikpapan city, where the oil spill in the Balikpapan Bay, and Lombok earthquake. We also join active and directly in the field to help to assist the disaster mapping. And then S.Si Indonesia initiative to help local government. S.Si Indonesia develop onemap.id to help local government share their own portals to their wider community. This portal also helps local government to learn from each other and adopt spatial-based solutions that have been developed in other regions. And this is our current webinar, but it end in 5 November. Maybe some of you has been joined one of this webinar, I hope. And this is a professional development training for the user if you want to learning about geospatial technology in ArcGIS. And last, that's for my presentation. Thank you for the time from Mr. Budi. Thank you.
All right, thank you very much, Mr. Hafiidh Alfian Affandi from S.Si Indonesia. It's very interesting that what you presented. That many different technologies have been developed by S.Si Indonesia to support all coastal and oceans monitoring. All right, we are now in 9:31, so we are really right on time according to the schedule. We can still have another 2 presenters for now. So now we're going next to the next presenter, who is Dr. Nurul Hazrina Idris. Let me present the short biography of Dr. Nurul. So Dr. Nurul is the senior lecturer in the Department of Geoinformation, Faculty of Built Environment and Surveying, Universiti Teknologi Malaysia in Johor Bahru. And she is also a leader of the Tropical Resource Mapping Research Group in UTM, and also an associate member, associate fellow of the Geoscience and Digital Earth Center in UTM. She also do some positions as the visiting researcher in the Climate Change Research Center of Excellence in the University of New South Wales, Australia in 2014, as well as in the University of Newcastle, Australia in 2018 to 2019. She received the award for the Endeavour Fellowship in 2018 from the Ministry of Education and Training of Australia, and the UTM postdoctorate scholarship to conduct a postdoctoral study in the UTM, Newcastle University, for 1 year. She has led several national and international collaborative research in the past 18 years in remote sensing and its related technology applications. Her research interest is generally on marine remote sensing with focus on coastal altimetry data processing, physical oceanography from space, technology, sea level rise and climate change, ocean energy resources and renewable energy, and artificial intelligence in remote sensing. So with her rich experience and skills, we are really delightful to hear her talk right now. Please, Dr. Nurul, the time is yours in the next 40 minutes.
Hello, good morning. Can you see the slide?
Yes, it's appear now. Thank you very much.
All right. Thank you so much, Dr. Budi Siliosto Adi, for the opportunity to give a talk this morning. And I believe that this is our very first collaboration. And hope to see we can further our collaboration among UTM and Mulawarman University in future. Also, good morning to the co-speakers, Mr. Hafiidh and also Professor Shum, and the audience. Selamat pagi ibu-ibu dan bapa-bapa sekalian. So today I will share about the coastal altimetry over the Southeast Asia, and the presentations today is based on the research that myself and my team in UTM and also University of Newcastle before when I did my PhD before. So I will share some of the results that we have up to today. So the presentation today will cover the following topics: the basic principles of the radar altimetry, and then we will talk about one of the main issues in coastal altimetry, which is the land contamination. And then after that, I will show you how the altimetric signals or waveforms and classes looks alike in our region in the Southeast Asia. And after that, we will talk about the data accuracy and options of the data product, the coastal altimetry data product that we have. And finally, some explorations works. So satellite altimeter is a matured technology that has been providing a continuous monitoring of the ocean since the past 30 to 35 years ago. And there are so many altimetric missions has been put into the orbit. And today, actually, we can see the technology of the altimetry that can be, actually, we can divide that into first the low resolution mode or the LRM altimetry, which is based on the pulse limited footprint. So basically here, the size of the altimetric footprint is even larger. And we can, and many researchers has been discussing about the accuracy of the data, particularly over the coastal oceans. And then the second one is the synthetic aperture radar. So this is the advanced technology of the altimetry, which is a beam limited footprint. So we should expect a better observations from this SAR altimetry when compared to the low resolution modes. And there are the low resolution mode is it is on board of the conventional altimeters. For examples like the Jason series, we got Jason 1, 2, and 3, and then the series of the ERS 1, 2, and VSAT. But for the radar SAR altimetry, it is started around year of 2010 with the Cryosat-2, which is meant for the ice observations, and then now being extended on board of the Sentinel 3A and 3B, which is can be fully used for the coastal and oceans applications. And it is also actually worth to mention that Saral Altica is one of a remarkable technology which use the Ka band, and we can expect a better observations over coastal from these data satellites when we compare with the conventional altimetry. This is they usually use the Ku band and also C band. So the basic principle of radar altimetry is actually simple, which is based on the fact that the time is a distance. So the distance between the satellite and the surface can be measured when the pulse is traveling downwards towards the ocean and then upward back to the satellite. So we can transform that into the range parameters, which is also related to the distance from the satellite to the ocean surface. And we can actually also measure the orbital height precisely. And then based on these two parameters, we can actually infer the information about the ocean surface. But of course, we need to do some data corrections because of the signals are traveling from the satellite to the surface. They are passing through the atmosphere, and also we also need to correct the errors or the contributions from the ocean dynamics. And also other two parameters that we can infer from satellite altimeters are wave height and also the wind speed. This is the ideal altimetry waveforms. I call it altimetry signals. That is ideal, where we can usually observe this over a homogeneous ocean surface, which is usually further from the land or island, or usually rougher coastal sea states. And for the conventional altimeters, which is the red line, it should follow the brown model. Meanwhile, for the SAR altimetry, the blue line, this is also an ideal signals from SAR altimetry. This should follow we call it as a samosa model. So this is an ideal waveforms which can be well processed using the standard algorithms. And here is examples of the altimetry data coverage. So over the Southeast Asia, from 3 active satellites altimeter, which is adjacent 3, Sentinel 3A and 3B. We can see that we have a pretty good data coverage with those 3 combinations of the satellite altimeters. Now, let's talk about the issues on the satellite altimeters over the coastal oceans. So there are generally 2 major issues when we are dealing with the coastal altimetry waveforms, coastal altimetry data, which is the first is about the land contamination. And the second one is inaccurate geophysical corrections, such as the tides and also sea states bias. But in this presentation, I will talk more on the land contaminations. And here is examples of the altimetric waveforms that are observed from the conventional altimetry, which is from JSON2, and the SAR altimetry of Sentinel 3A. And the first figures here and also here are the ideal waveform that usually observed over a homogeneous oceans. So usually we can expect a good accuracy of sea levels measurement from these types of altimetric signals. But over other patterns are also observed. These are the others is the coastal waveforms, where we usually see these patterns when the satellites are close to the coastline. So we can see an obvious how the waveform shapes are deviated from the ideal to so many patterns, other patterns. And actually, the high peaks there are the reflectance from the land. So it's kind of a mixing between the ocean and the land signals. And this is actually happened when the altimetry's footprint, here's examples of the altimetry footprint, where it receives signals both from the oceans and also from the land. So within that, the simultaneous view of the altimeter in a footprint, so the signals from the land is also being represented in the signals. So usually we should expect that the data from these signals might be inaccurate. So we need to be carefully use the data. But there are actually techniques that is called as a waveform retracking that we perform on the ground to recover or re-optimize the geophysical parameters. This is usually been conducted on the land before. This is sort of a data corrections to make the data, to recover the corrupted data. So just imagine that we have a signals coming down and return back to the satellites, and if if it is over a homogeneous ocean surface, then the signals or the altimeter waveforms will usually like something like this, and from these waveforms we can actually retract or model them based on the standard techniques, technical algorithms, or standard retracking algorithms, and we can get accurate information that is related to the sea levels, which is in the middle of these signals, the sharp rise. So that's the middle location is related to the sea levels. But in a case when it is over coastal, for example, this is a waveforms over coastal with the impact of the lands there. And then let's say this is the locations of the actual locations that is related to the sea levels. And then we retract that using the standard model, okay, like a standard model. So basically, the locations of the sea levels has been shifted, and we can use the altimetry waveform. We can use the retracking techniques where we can correct these errors by applying the more appropriate model. So from there, we can re-optimize the estimations from the onboard satellite systems. Now, let's see some examples of the waveform patterns over the Southeast Asia. This is examples over North Kalimantan. And we plot two tracks, which is from Sahara Arctica and also from the JSON2. And here we can see that the waveform, the ideal waveforms from the Sahara Arctica exist beyond 2 kilometers from the coastline. Meanwhile, it's about 6 kilometers from the coastline for the JSON2. So this is due to the fact that the size of the JSON2 footprint is even larger than the Arctica. So JSON2 is using the KU band, meanwhile Arctica is using KA band. So the size of the altimetry footprint is slightly smaller for Arctica. So the impact of the land is not as severe as on the JSON2. And here is another examples on of the waveform shapes for the SA altimetry. So actually for SA mode altimetry, we can expect that the data is even better than the conventional altimetries because it could provide higher resolutions of the data. And we should be able to get the data much closer to the coast. But that expectations of the high resolutions about 300 meters is we should expect this when the satellite direction is along the satellite tracks. So but different cases we see different performance when the satellite is nearly parallel to the land, where usually the spatial resolution across the satellite tracks is similar to the low resolution mode of altimeter, which is around 7 kilometers. So because Southeast Asia has so many islands and lands, especially like Peninsula Malaysia, in which the orientations of our peninsula of Malaysia, the orientations of the land is nearly parallel to the satellite tracks. So we tend to see that the resolutions is only about 7 kilometers. So this case over Peninsula Malaysia is also similar to Sumatra, where the orientations of the Sumatra is also parallel to the satellite tracks. So for examples in this diagram, we see that coastal waveforms appear within 7 kilometers from the coastline. It is not up to 300 meters. This is when we plot the distributions of the waveforms over the Southeast Asia. So the red one is the coastal waveforms and the gray one is the oceans waveforms. And we can see that over Indonesia, especially over this part, where there are so many coastal waveforms there. So this means that the data should be used in caution. Because when we further classify these waveforms, we got 3 different classes. So class 1 is the ideal waveforms over open ocean. So we should not see any problems with that. But for class 2 and class 3, especially class 2, it appears so many within 2 and 4 kilometers from the coastline. So it is pretty crucial for our region in the Southeast Asia. Now, let's see how accurate is the data. So we will have a look at the accuracy of the conventional altimeters first. This is when we plot the percentage of valid data or data coverage over the region from the standard product. So the blue one is when the data coverage is less than 50%. So, and again, we see that this is a problematic, this is the regions where we saw less data coverage. This is from the Sara Altica. And we further analyze the data that we have by dividing the regions into 5 seas. So we got Andaman Seas, Gulf of Thailand, Strait of Malacca, South China Seas, and Sulu Sea. And here we can see that the Sulu Sea has the lowest percentage of valid data, meaning that it has a low data coverage due to the shallow water and complicated area. And here it shows that the data is only available probably beyond 4 kilometers from the coastline. But differ from the South China Sea, where it is a less complicated region where we could get better data coverage, and the data can even much closer to the coastline. And here is examples when we conducted the comparison or validation with data type gauge at 1 stations in Kota Ponoi station. And this area is actually less complicated. So we could find a pretty good agreement between the altimetry and the tight gauge data. So we calculate the correlation of the data, tight gauge data with three different retracking algorithms. So this data is basically can be obtained in the standard data product. But we found different findings at Langkawi Island. So Langkawi Island is situated at the Strait of Malacca, where we cannot find any relationship between the tight gauge and the altimetric sea levels. So when we look at the signals of the altimetry, here we suspect that this is due to inaccurate geophysical corrections, particularly the tides. And these tables actually shows when we conducted some analysis to compare the sea levels, the detiding techniques from different detiding models. So actually these techniques got GOT 4.7, FAST 2012, and DTU10. We can get this data in the data products. But when we apply that, we can see that the standard deviations of the SLA residuals within 5 kilometers is still large, which means that there might be the tidal signals being left in the altimetric signals. But pointwise techniques is a technique that we use based on the Anderson technique. So through that technique, we could be able to get slightly better for the purpose of tidal corrections or detiding techniques. For the accuracy of the SAR altimetry, so here we first made a comparison with the geohike. So, and we computed the standard deviations of the residuals between the Samosa plus retract sea levels with the geohike. So we found that within 6 kilometers, the residuals is pretty large, which is more than 100 centimeters. But it is improving when we get further from the coastline. Here is examples of the sea level profiles that we plot from different algorithms. And this is when it is crossing the coral atolls. So we see that it becomes noisy, and some of the algorithms that being used is misestimated the sea levels. So this is also one of the problem when we use the satellite altimetry over coastal oceans, particularly when the area is having a coral. And we compare the standard data at one of the target stations in Kolak, and we found this is pretty good agreement actually with the data type gauge. So let's say if one is intended to use the altimetry data for coastal explorations, what might be the options that we have? So in the Aviso website, actually, we can opt for a coastal altimetry product instead of the standard altimetry product. So what is a coastal altimetry product? In the Aviso website, we can get a free access, this freely download to the Pistach product, which is the Pistach product is for JSON2, and PK product is for Saral Altica, and also ALES. So these are a good choice of the altimetry data for coastal applications. And for the Sentinel-3 A and B, it can be downloaded through the GPOT, European Space Agency's website. And this one, the broad view radar altimetry toolbox, is an open source software where we can conduct a basic processing of the radar altimetry data. But here in this presentation, I would like to share the systems that I've been developed over the past 10 years, which is we call is as the chorus. So chorus is stand for Coastal Altimetry Waveform Retracking Expert System. So in this system, actually, we are trying to optimize, we're trying to produce the accurate sea levels, particularly over coastal, by combining different retracking algorithms. And we use the fuzzy expert system to make decisions on the data analysis. So the system is actually got two important operations. The first is it search the optimal retracker to reprocess the waveform, and that is assigned based on the analysis from the fuzzy inference system. And second, it minimizes the relative offset in the retrieved sea levels when switching from one algorithms to another. And we introduce the neural network to these solutions. And in this system, actually, we introduced the neural network technique to handle the issue of data offsets. So why is this crucial? It's because we combine different sea levels from different retracking algorithms. But the thing is, combining different retrackers is not as straightforward, because it got an offset between different techniques. So we need to remove that. Otherwise, the final output of the sea level will have a jump, a big jump, and it is will affect our data accuracy and the data precision. For examples in this figure, so the red line is from the one of the algorithms, retracking algorithms, that is called as the threshold. And the green one is the standard techniques, the standard retracker, which is the MLE4. So we can see that there are obvious bias or offset between those two algorithms, which is probably nearly about 40 centimeters. So we cannot just simply merge these profiles. And the neural network is introduced because our analysis has found that the value of this offset is a function of the significant wave height. So that the offset is not constant, but it is variables which is varies with the variations of the significant wave height. So here we introduce a neural network technique. This is how the chorus generally works. Okay, let's say that we have the waveforms data. We will process the waveforms data, and then we will bring it into the neural network framework, where we basically train the neural network based on the waveform, the sample data samples. So in chorus, we consider three techniques, retracking techniques. The MLE4 is the standard retracker. A sub-waveform is the coastal retracker that we developed back in 2013. and modified threshold with different data percentage. So we will train this, and basically in this framework, what will happen is that we try to learn about the relationship of the offset among those data, so that we can remove that later on. And the output from this framework is the trained neural network. And here we also classify our waveforms into here 6 classes. And then what we do is that we define the retracking precedence and prioritize the retrackers based on the classes, the waveform classes. For examples, that for class 1, we will retract that using the MLE4, and then after that sub-waveform, and then after that mode threshold 30%. And so this is basically shows that the chorus will actually go through 3 times of iterations. For examples, during the first iterations, class 1 will be reprocessed using MLE4, and then class 2 to 5 using sub-waveform, and class D using the mode threshold, the 30%. And this will, during this first iterations, it will come to produce the sea level anomalies. And then there we will apply the trained neural network to remove the offset. And it will bring to the fuzzy inference system to analyze the quality of the data, the sea levels. And here it will make the decisions. If the data is having a high quality, then it means that we will keep the data. Otherwise, it will go back for the second iterations to be reprocessed for using the second prioritized retrackers. And these systems will goes on until the end. And this is examples of the output from our chorus. So we can see, so the top figures here is the sea levels. And the bottom here is the quality that we analyze using the fuzzy inference system. So here the black line is during the first iterations, blue is the second iteration, and green is the third iterations. So you can see during the first iterations, there are several places where we found the data is having a low quality. And this is also represented by the noisy sea level profiles. And during the second and third iterations, the chorus will try to improve the data quality and also improve the precisions and the accuracy of the sea level profiles. So that green lines is the final output. So you can see how it is being improved from the first to the third iterations. We then conducted some accuracy assessments to analyze the output from our chorus. So we're pretty happy with the performance at this stage, where we found the more data coverage, more valid data over the Southeast Asia using the chorus system when compared to the standard data. And we can reduce the data gap even closer to the coastline. And this is example, the tables of the tight gauge validation, where we assess the accuracy by comparing with 9 tight gauge stations around the Southeast Asia. And we found that chorus is better than MLE4 and ICE1. This is the standard retrackers at 6 out of 9 cases. And the correlation is reasonably acceptable. And the RMSE is smaller than 20 centimeters. So we're pretty happy with the performance of chorus at this stage. And here is just another examples of validation at station Kota Punoi. And we see here from this table where, actually this temperature correlation, we slice that into several coastal or distance bands. So we can see that the standard MLE4 is unavailable for the when it is become very close to the coastline. Meanwhile, Chorus and also Chorus has good agreement with tight gauge. It's performing better than the ICE1, but we see that in some cases where ICE1 is also better than our Chorus system. So now this is some of the applications that we have been conducted using the coastal altimetry product. And the first applications is that we studied the coastal upwelling. This is in this study we use the Altica data. Actually, first we map the sea levels, and then we overlay that using the wind speeds and the directions. And from this study, actually, we plot, we observe the coastal upwelling event over the east coast of Peninsular Malaysia, which has happened very close to our coastline. So it's basically happened, the events is developing from June, July, August, and also in September. And our second applications is on the ocean renewable energy. This is, we joined with the team of marine engineering, where we use the Altica data for assessing the wave energy resources in Malaysia. So here we could be able to estimate the wave period based on the significant wave height from the altimetry. And then we could estimate and model the monthly average wave energy in Malaysia, so that we can learn the climatic conditions. Here's the climatic conditions and the estimated wave energy that we might expect. And through the study, we could identify the zones that have a high potential as a wave energy farms. So at least we understand where is the suitable locations when our government is intended to have a wave energy farm in Malaysia. And here is another ongoing explorations work under a research grant from our university, which is on the coastal vulnerability assessment towards the climate change impact. So in this study, we use the coastal altimetry extensively for quantifying the coastal sea level rise together with the tight gauge data. And then also to analyze the wave height variations and the tidal range. So in this project, what we are looking forward is to hintcast and also to forecast the climate conditions in Malaysia, and to look at how vulnerable our coastal. So in summary, the standard altimetry data, for example, the MLE4 or ICE retracker, is found insufficient for coastal oceans at the Southeast Asia, and it has low percentage of valid data and large no data gap, probably beyond 7 kilometers from the coastline. So for coastal explorations, considers using the options of coastal data product, such as Pistache for the JSON2, Piki for Sara Altica, ALES, or also Chorus. I think I get to the very last slide. I would like to take this opportunity to invite all of you to Johor Bahru, Malaysia next year. We are hosting this international Asia Pacific conference on the 15th Pan Ocean Remote Sensing Conference. It has been postponed. We do not have a new date yet. Because of the COVID, but we still open for the abstract and also the physical tutorials. And coming soon, in addition to the physical tutorials, we are holding also an online course on ocean remote sensing towards a resilient climate in February 2021. So we are open for registration. And also it is good to mention that we do have scholarships to support the traveling, particularly for early career scientists and also students from developing countries. So we hope to receive applications from Mulawarman University. Okay, I think that's all. Thank you so much for your attention. Thank you.
All right. May we give some applause to Dr. Nurul for her very comprehensive presentation. We learned a lot about the satellite altimetry and the development and the recent development that you already been doing. So again, we learned a lot. So thank you very much for the talk.
Thank you.
And if you don't mind, I believe most of the participants will be very happy if you could share the slides to the participants, maybe in PDF format or something.
Yeah,
So
sure.
again, we really open for collaboration research, Dr. Nurul, especially with my background with satellite altimetry for the inland water. So we still have very much less research on that topic. So I believe we will have very good collaboration in the near future.
Yep.
So today we also already have Professor Shum, and we also have here Dr. Johnson Lumban Gaul from IPB University. I believe Dr. Nurul also know him very well.
Yeah, very
Because
well.
he is also one of the leading scientists in Indonesia for satellite altimetry. And as an additional information, we are now trying to develop a kind of community for the satellite altimetry scientists in Indonesia. So ranging from the coastal applications like Dr. Johnson, me for the inland water applications, and many others for geoid, and various other applications from ITB University. Well, I believe this is kind of a little bit hard topics for most of the participants, because most of them are coming from geospatial science or even general science. So your explanation about the introduction on satellite altimetry will be very helpful. Okay, without spending too much time, can I check the audio and video for Professor Shum?
Yes, hello. Can you hear me?
Oh, okay. Thank you very much, Dr. Shum. It's very nice to see you again after
Nice
about
to see you.
almost 7 years right now.
Oh, is that long?
Yeah.
Okay.
All right. So Professor Shum is a professor and a distinguished university scholar from the Ohio State University. His expertise is more on satellite geodesy, sea level, satellite oceanography and hydrology, geodynamics, and ice mass balance. He's really one of the leading professor in the field of satellite altimetry. And I also learned a lot from him during my PhD in the Ohio State University back in 2009 to 2013. So thank you again, Professor Shum, for that moment. He's also contributed in one of the Nobel Prize awarded to the IPCC and Al Gore back in 2007. He's got a lot a lot more awards, including the Fanning Mains Medal from the European Geoscience Union for the research in geodesy applied to sea level science in 2012. And he has published over 300 journal articles and book chapters in various leading journals in the world. So I believe CK has more things to convey today, and we will be happy to see your presentation.
Okay, so I should share the screen, right?
Yeah.
Yeah. Let's see, share the screen. So should it is share.
Right, the slide is appear already.
Okay.
And
so
you have about 40 minutes for your talks.
Okay,
during
I'll
the
be quick. Well, thank you for the invitation. What I'll be talking about, although the topic of the conference is altimetry, actually I will go beyond altimetry, and I will just do a very quick introduction, because I try to save a little bit time and didn't write down a lot of words on summary. So Dr. Idris, is that how you pronounce your name? Very nice talk. So she's been working on altimetry. So for example, this is the JSON2 satellite, Topaz. So it's on here, and Cryosat2 is also one of them. I will also be talking a little bit about the gravimetry, spaceborne gravimetry. Actually, this is the GRACE follow-on satellite that you see. And also I'll be talking about a little bit about synthetic aperture radar, actually dedicated to actually work on wetland with vegetated wetland sea level. And then another topic I wanted to touch is actually GPS or GNSSR, but it's the refractometry. So this is the so-called multipath that everybody geodesists want to get rid of. So this is becoming a very hot research topic, and the signal is not big. So I just have some examples. So the topic over here is that it doesn't really matter what sensor that we wanted to use, but the focus now is something on an application, meaning we wanted to actually detect, find the feasibility of using these sensors or combination of these sensors, try to monitor, for example, water resources and flood and so on. So actually I should probably skip this slide, but this is the principle of satellite altimetry over ocean, actually over lake as well, and even over land or ice sheet. So we have this repeat orbit. So this is actually the picture over here is JSON, sorry, is Topaz, actually the really old 1992 launch satellite, and then JSON's over here. So basically this is a repeat orbit. The so-called repeat orbit in here is like 10 solar days, about 9.9 sidereal, 9.99 sidereal days. So we want these pixels to overlap on each other, so we could make changes to the ocean, sea level, changes to the hydrologic lake level, changes to the water level, and so on. Actually, that's easier said than done. And I could just, I'm not going to go into details. In the ocean, we know very well, in the deep ocean, like Dr. Idris was talking about coastal ocean, that's a very tough problem. And with large lakes, you get a lot of data products in altimetry. No one actually tried to remove the gradient, and also on wafers. So this is a research area, probably like Budi's research area. All right, so you have the track. So I wanted to talk about some applications. We actually done this quite a while ago. 2008 is a former student, Hongki Lee. So this is a dam in Turkey. It's the very big dam at the upstream of upstream from Syria and also Iran and Iraq. So a track over here, color coded, is actually the height. So you basically could sort of measure the water level across this dam, but obviously there's going to be a very variability. Anyway, so what I want to show this is that it actually monitor people changing the water level, meaning anthropogenic. So the river over here, the lake over here was dammed up to become a reservoir or dam. And then the water start filling in because they have to rely obviously on rain. So you could see this is human filling in water because they dam everything up. But then you could see this annual signal. So these are natural. So when you have a rainy season, it goes up. Dry season, the other part of the season, it goes down, and so on and so forth. And then you see the drought over here. So this is actually a drought, not really that they let go of the water, you know. So these actually has applications in terms of water security, water policy, and so on. And I could give many more examples. So we actually did a project recently with NASA over here. We, along with Mike Durang, who's a hydrologist at Ohio State University. So all these points, so these are the data we call virtual stations. This actually is an animation, but to save time, so you could put it on a Google Earth. So here's the Google Earth, and then I'll show the later on another visualization, but I don't think I'm going to go to the web. So basically, each of the points. So we have dams in India, for example, Bangladesh, and over Tibetan Plateau, and it's actually all over the world. So you for different, for example, for this dam over here, this white dot, you could see the seasonal variation, and so this is MV set. Another MV set outtaker, which is following up with MV set at 35-day repeat in the Kushner wafer over here. So right here, and then another dam over here. So this is also the Kushner wafer, but JSON too. So we have multi-satellites. All right, so this is a screen dump of the web. Actually, if you type, let's see, is it here? Oh, okay. So here's the link. If you click it, it's called Altimeter Virtual Stations, and this is an abbreviation. You'll get to the next one. Actually, this is, but this only has currently large wafers. There's no dam and other things. So you could actually click on each one of them and then get a time series, and you could download the data. All right, so quickly. So I wanted to now talk about this gravimetry, and the whole acronym is Gravity Recovery and Climate Experiment. So the short term is called GRACE. And now 2018, NASA and Germany, GFZ has launched the GRACE, the so-called GRACE follow-on. So if you look at these, this is a satellite over here. I'm just going to illustrate basically these two satellites separated by several hundred kilometers, and the altitude is about 500 kilometers. And then there are two identical satellites, and they could be actually interchanged. They they did that after the satellite gets old, they switch over. This becomes the first satellite and the other one becomes the second satellite. So the measurements actually this invisible radar link. For Grace Follow-on, they actually have a laser as well, the laser link. So the accuracy, the precision of this link is micrometer. For laser, it's supposed to be about 30 times more accurate. So let's see, maybe I'll skip the equations. Basically, this is one technique where you actually measure the change of the potential. The JPL engineers who build a spacecraft has a nickname for these two satellites. They call it Tom and Jerry because the satellite is like the cartoon. The cat and the mouse, the cat should never catch up with the mouse, otherwise it's game over. Cartoon will be over. All right, so long story short, so this is one scenario, only up to about 14 years of data. So this is one graph. Sometimes it works, sometimes it doesn't work, meaning that we fit a slope or a trend of the time series. So in a way that's, for example, in Greenland, you could see the ice melt in Greenland, and then West Antarctica over here, and then Antarctic Peninsula. East Antarctica, you actually see gain because there are a lot of snowfall. For hydrology, we don't have trends, right? So, but however, because of the short time span, sometimes you could see this signal over here and signal in the Midwest of United States is actually flood signals. So this is a 2010 Mississippi flood because signal is so large, it looked like a trend. So this is the Alaskan Glacier. And these two regions here are actually groundwater depression. So it's the Middle East. And I'll have a little bit more detail on the water resources side of the application. So you could do a lot of interpretation, but one thing I would do, okay, it's not here yet. So there's examples of glacier. So this is the so-called high mountain glacier. By the way, this number gets slightly larger as you increase the time, but still, so it's 5 gigaton is a lot, minus 5 gigaton per year. So over the span of about 14 years, you could see the seasonal, and then it's basically mostly losing, the ice is losing, melting. The only glacier system that's basically advancing is the curriculum in near Pakistan and the Western Himalayas. The rest of the world, all the glaciers are melting. So Budi, you may want to tell me the time. Hopefully I won't go over too much. So Canadian Arctic Glacier, so it's minus 58 gigaton per year, huge melt. So now I show this one publicized applications of the GRACE satellite. Is basically its ability to sense something underneath the earth, like groundwater, right? So as we know, we don't have any whole lot of ways to measure it, except you dig well deep into the earth, you can measure the groundwater. So there's a caveat, there's an assumption over here that, so this is, let me show all the regions. So this is the old result, only up to 2017 or so. So for example, this area, this is at the foothill of the Himalayas in India. And this is there's another region that's not shown a time series. So basically you could see the groundwater is depleting. How could you compute all the groundwater? You have to know the surface water and subtract it out from the GRACE data. So GRACE is gravity, it sees everything. Whether it's ice, whether it's earthquake, it sees everything. And you could see this Australian Artesian plane aquifer, you could see very strange depression of water suddenly recharge and go up and then come down again. So the trend over here that you see on a figure does not really do any justice to this kind of phenomena. You can't tell unless you actually look at the time series. And this aquifer in South America is sort of the same, very interesting. It has very good seasonal signal, but sometimes it's small, meaning rainfall is small, the recharge is a lot smaller. The high plains in the United States actually is one of the largest or the largest aquifer. You could see very complicated, like drop down, draw, and then coming up again. So so we talk about hazard. So land of water is also hazard, and groundwater is a drinking resources. Is very important for irrigation. Basically, I don't think it's a problem in Indonesia or Malaysia, right? You have a lot of water, and okay. So let me do some close up and a little bit more detailed work. So it's basically these 3 areas. So we were interested in Bangladesh. So this is the nation boundary, and Performocha, one of the largest basins in the world, and then Indus River basins over here. So you could see all these complicated groundwater is actually groundwater storage is in red. Again, we have to remove a model which is SM. It's like soil moisture. TWS meaning GRACE data. So you have to know, so if the model is wrong, your groundwater is wrong. All right. So pretty famous hydrologists publish a lot of papers on this. All right, so the other thing we're talking about floods. So this is still the gravity data. And if we process the data in a way that we only, instead of monthly solution, for those of you understand the GRACE data is only like monthly. Here we just like make 10 or 11 day solution from level 1 data. We do our own immersion and then we move over 1 day. So this is basically an example that we could actually, see the evolution of flood. So here on the green or the light blue, these are droughts. So for example, in this region in Bangladesh, they actually have droughts every year. They have a lot of water in the same year, and it floods, for example, 1/3 of the country. So this is drought in India. What I'm gonna show is like 2008. This is there's a huge Indian flood, Indian continental flood, actually originated from Bangladesh and Myanmar. So you could see the huge, so there's a lot of water. So GRACE actually measure the weight of the rain on the land and create actually the loading effect. So the crust moves and GRACE is able to catch it. So the signal is actually quite small in terms of gravity unit. So with this, you can actually look at evolution of the flood for in a day. So this huge flood actually lasts pretty long. So you can actually map it very well. I actually did something in Indonesia, but sorry, I couldn't find it. I could send it to Budi later. So try to look at a flood. So keep going. So this is our satellite altimeter application. So I don't know whether you know this term. It's called land cyclone or land hurricane. So this is the city of Chicago in October 26, 22, 27, 2010. So basically, this is like a cyclone over land. Well, people said this is because of climate change. So this has one of the lowest barometric pressure even for hurricanes over the ocean. So the idea is that we wanted to see whether we could see these signal over the Great Lakes using satellite altimetry. All right, so this is the, so you could see it's like a hurricane, but it's over land, or cyclone is over land. All right, so I'll skip over these. So now I'm gonna do a little bit detail. So this is actually not all the altimeters we have. And since it's October 2010, some of these satellites are no longer there, right? So the yellow lines you see is 35-day repeat. And the red line you see is the topaz JSON, is like 10-day repeat. So you could see the spatial, so when you have more frequently sampled data like 10-day repeat, you lost in space, so you cannot cover the whole Great Lakes. So this is Lake Superior, the largest lake of the Great Lakes system, which is the largest freshwater lakes in the world. And then we put in Sentinel-3A. Actually, Sentinel-3B is also like there, so you could see the green line. It is, I believe, it's 28-day repeat, right? So you have very different temporal distribution of altimeter and in space. And then our idea is, what our hypothesis try to say, oh, you got this hurricane on land marching through this lake here. So all the river, all the lakes would be a lot of wave. We want to see whether we could detect it. So actually we could detect it like with this ascending path. So meaning the satellite, JSON to satellite goes up and come down again near the edge, the eastern edge of the Lake Superior. So I'll show the results. So this is a result. Actually, it could have been plotted a little bit dramatically, meaning changing the scale here. So you actually, so this is the lake pass for JSON 2, but it's not during the storm, and this is not during the storm either. So this is actually during the storm, and this is all the storm has passed. You could see by your naked eyes that this seems to be has higher variability. Okay, so but the signal is only about 9 centimeters deviation. You know, if you compare with like 6 centimeters, you know, normal times. All right. So this is a visualization of like before the storm. So you have these color-coded passes, but during that storm, you can actually see these sort of 9 centimeter up to 10 centimeter changes. But this is lucky that altimeter could see it. So basically it's an exercise. So if you detect it, so what, right? You can't really see all this evolution of these storm signals. All right, so let's move on. So can you actually see grays, which for this particular typhoon, it's called Vincenti, that went into South China and so on. So by the way, gravity grays is like 300 kilometers half wavelength. So the pixel is 600 kilometers. So versus radar altimeter at several kilometer footprint. So this is like 2 orders of magnitude, 2 cores, right? So however, you could see during the time. So this is basically rain hitting on a solar Earth, and then the solar Earth responds because of elastic loading, and the gravity satellite measures it in space. All right, so let me move on. So this is basically making each day marching through, and you could clearly correlate the red, which is a lot of mass gain, with basically with a storm with a lot of rain on land. Oops, sorry, this is not supposed to be there. All right, so I want to quickly talk about this new technique. so some of you may know, so this is an exaggerated GPS receiver, GNSS receiver on land. Obviously, it's not going to be that high. So basically, you have multi-system GNSS. Basically, let's just take GPS. So it had a reflection over here, and then it bounces. And then this receiver could catch the multi-path signal. For example, if it happen to be bounced on the water, then you could measure sea level. It bounces on a water, a lake, you could measure lake level. If it bounces off like snow surface, you have a chance to actually get snow depth. So this is the so-called signal and noise ratio method. The first person who wrote a paper on this is Christine Lawson. She retired already, University of Colorado. So basically, a very simple schematics is that you need to know this geometry, and then you also need to do filtering of these. So it only uses one frequency, right? A phase data. So you have to really know what the signal in the ocean is, and then do a periodic-gram and filter out. So I want to talk about the satellite. So Cyclone Cyclone GNSS is a NASA like X-satellite constellation, but it's only like single frequency. So it's supposed to study the wind speed. And some of us are try very hard to do altimetry. But the cold range altimetry, the accuracy is at a several meter level. But you can also do like phase altimetry, which arguably could be under 1 meter. So this is research ongoing. All the data are free. And so for some of you who are interested, you could look into this. All right, so I would do a very quick, well, let me skip on a theory and show you some results. So this is a student, Jason, did his dissertation in 2017. All right, so what he did was so this is Lake Huron. We talked about the Great Lakes. So there's a GPS receiver next to the water, next to the lake, and then it also has a water level gauge. So you could see the so-called tide gauge is water level gauge. Don't know whether you could see it. The color is not very good. It's the black line, and the GPS water level gauge is following it. So there's a lot of filtering. Long story short, the data are quite noisy, but if you filter it, if you make monthly averages, it actually has something like 15 years of data. The comparison is about 1.2 centimeters. This is over the lake, right? It's the best case scenario. All right, so I wanted to proceed and talk about the last topic. How am I doing on time? Am I okay on time, Woody?
That's okay.
Yeah. All right. So, so this is a general statement, and I won't show everything. So we could use radar altimeter, actually sympathetic aperture radar. I wanted to talk about how do we do that, and this is not a conventional technique. So the science is that ash trees and river ties. I know in Indonesia there's a lot of mangrove forests as well. So some of the SAR has to be probably L-band so that it could penetrate and hit the water. You know, double bounce scenario, you'll see that. And then the GPS reflectometry, and you saw before. So I'm gonna do some examples of ties, you know, Amazon and poacher, and then move on to the Sandarbon, which is in Bangladesh wetland. So here are the points in the Amazon. These are the tracks, and I want to be a little bit quick. So on the first point, which is a JSON point, we did a tidal analysis. So this is the altimeter data, and then we use the data to fit ties. But see, this is like way not in the ocean, in the river, right? So actually river ties is pretty big in the Amazon. So this is a very good scenario where you actually make a 75% signal reduction if you do ties. So for those of you who are doing wafer hydrology, actually you have to remove ties because they would contaminate your hydrologic signal, your discharge signal, your storage signal, because it is topography track. So here's another JSON tool. Actually, this is even better signal reduction, meaning that 90% of these altimeter data which is improved are really ties. All right, so let's move to the Bangladesh region. So this is Dhaka, this is Bay of Bengal. So here you also see a 75% reduction for JSON 2, and you see a 95% in MVSAT signal reduction. So this is just an exercise using radar altimeter. By the way, the point is way inland. There's no time model here that's valid in here. So these are two examples. The other examples, like is pretty famous, is Colombian wafer in the United States, and elsewhere they have ties. So I actually see it with my naked eyes. I think is around here. So you have the wafer in the winter time, and so before we go out to lunch, the height is pretty big. After we came back, actually you could see the bottom of the wafer. So that it's about a meter down, and there's no other mechanism except ties because there's no gates stopping the wafer. So this is a tremendous physical phenomenon. All right, let me just do this very quickly for the GNSSR. So with Altimetry using SNR. So my student Jensen did the work. As I said, Christine Lawson is the first person who published this in 2013, not long ago, 7 years ago. So this is actually, if you're familiar with the geography in the United States, I should make a plot. So this is Western United States. Seattle is a city in the state of Washington. So there are two stations, there are two GPS points. Somehow it's very close to each other, only 38 meters. So that's the number 5, RPT5, RPT6. So this is 38 meters, and then this is in Tacoma. If you ever land in Seattle, you get into the airport. It's called the Tacoma Airport. So this guy is actually near the ocean also. It also measures the GNSSR. So we could use this technique to measure water level, actually away from the ocean. So the idea is that, so actually we'll find out that the sea level over here does not really agree with this sea level because of the tides. That's our hypothesis. But we actually have no way of telling, have another explanation, because you need a model, because this is a very small area. You have to really do a time modeling, hydrodynamic modeling to verify it. So I will just show the results. So if you recall, the tide gauge is about 13 kilometers away. So you could see a large difference actually. And these two is like about 38 meters away, pretty close to each other. So you could see the light pool, the tidal signal differences is like half a millimeter usually, you know, like less than 1 centimeter. So it's basically agreeing very well, but again, away from the, let me just show this again. So what I'm trying to say is that we use the data, the time series to do ties. The time model over here, and the time model over here disagrees. So we argue that these data, these two actually have different ties. All right, so let me go to the last topic, which is the synthetic aperture radar backscatter. So the terminology called backscatter, meaning just actually exactly the same as radar altimeter. By the way, radar altimeter has SAR altimeter as well because it's delayed Doppler. But synthetic aperture radar actually look to the side, it's not the nadir. So this is elementally SAR sort of refraction physics. So when the radar signal reflect on this big tree, it could be mango forest. You just get out, so you have no data. And then you also do these different refraction, it gets back. You can only measure the tree top. It's called volume scattering. Somehow, if your signal penetrates these trees or these herbs in a wetland, so you hit the water, and the water bounces to hit the tree trunk, and then go back and satellite catches it. This is called a double bounce. And so basically the explanation is that if you see the blue line of water go up, this signal from the backscatter will be different. So in that way, you could actually measure this the so dB of backscatter, and then build a relationship. You could actually measure the water height change in the wetlands. So it only works for that with a lot of trees and wetlands have this mechanism. So we try to see a hypothesis, see whether it works. So we talk about tides, right? So this the Sandarbans is the wetland, and mango forest is a huge region. So this is a picture of the high tide. Actually, I'm not sure whether the same picture. I grabbed it off the web. I think I acknowledge it, yeah, here. So this is supposed to be same region, and then low tide. And this happens twice a day and once a day. So because the tide has frequencies of 12 hours and 1 day. So here's the region that we're talking about. So this is region, well, it's Bengal, right? Bay of Bengals. You have the Bengal tigers. I don't know whether you know. I think there are tigers in Indonesia too, right? Malaysia, the tiger swims. I don't know whether the tiger in Indonesia swims or not, but I believe it's only place that the tiger swims. If you throw a cat into the water, I think they will die. All right, so let me just go through it quickly. So here a study area. We actually uses the altimeter combining with a SAR because remember we have to build a model. So to build a model, you have to calibrate the backscatter amplitude with some real height. You could obviously use a tide gauge to do that, but there's not a whole lot of tide gauge. So here's the mango forest. You can see it's very complicated, and we have 2 tracks. So I won't bother you with all these SAR since this is done by Yuan Jia, our research associate here. And this is like Japanese pulsar. So this is L-band. So L-band actually could really penetrate. So we have problems with C-band. Not to mention X-band would not work. Okay, I'll just skip over about all these slightly, it's not detailed actually, but the flow chart of how to do this. So again, this is not doing INSAR, but INSAR is also done try to classify the vegetations and so on, which I won't. So this is actually an animation. Oops, sorry, let me show the animation. So we have about 20 backscatter coefficients. So this is dB over here. And as I said, it translates into, somehow it stopped. Okay. So you could see that it flashes through. It is non-evenly spaced time. So you could see actually complicated change of dBs, which you could translate into water level. So this is just an animation of the signal, and it repeats over again. So what we did was actually we want to go a step further. We try to build a time series, and then we would do time models. So we actually use the satellite altimeter over here at these points to make a model to basically, when you measure the backscatter coefficient, we change it to, we use the model, a linear, inverse linear relation, you change it to the water level change, right? So that's the model over here. So I just show about 6 of them. Remember, I have 20 of them. So you could use a composite model, or you could use every different model. They are almost the same, the regression. So this is a very good one. This is okay, this is okay. This is not so good. And this is better than this, but not so good. And this is okay. So we basically build a model. You could see that vertical axis is actually what was measured by the satellite. So you have an inverse relationship with the height, meaning at -7, let's just say dB, and then this is like 0.8 meter water height. So the variation actually goes pretty high. So it's like 2.2 meter to about 0.8. So about 1 meter fluctuation of the water is pretty high. Actually, it's because of tides.
Excuse me,
So
CK,
we actually make a composite model, and then you could see with averaging, although the error bar is big, somehow these average water. So here's our model. So what we did was we used each of the 40-meter resolution water level height change, and use, this is the SAR data, and then try to build a water time series in the wetlands.
Excuse me, CK, you have another last 2 minutes.
Okay, all right, so finishing up. So I just want to show you the tides, actually the red line is estimated tides and so on. So you could actually see different points that we have there. So each of the points to show, but actually the time model is valid over this region. I think we average to about 100 meter sort of spacing, but still is pretty high resolution. I think this is it. Thank you.
Thank you very much, Professor Shum, for the very interesting talk. And this even make our context wider from just the satellite altimetry. We go through SAR techniques, even the GNSS reflectometry, which is really interesting. And at the end, you wrap it up with the combinations of these topics. So thank you again for your kind willingness to give us a talk, to give talk to our webinar. So now we are coming to the question and answer session. We used to have about 20 minutes to 11, but now we're already at 11. So let's see how many questions we can cover during these sessions. There are a couple questions that already been asked. For example, the one asked by Pak Suparjo from Indonesia. But it's already been responded by Dr. Nurul already. So Pak Suparjo was asking about what's the techniques, or how can we combine the techniques that we talk about today to study about the earthquake. So if you have some insights on the earthquake, maybe you can give us some information, Professor Shum.
Oh, using altimeter to detect earthquakes? Is that the question?
Not just altimeter, but any others.
Okay. As a matter of fact, this will be the forefront of the research. I think large earthquakes is actually possible if you try to use altimeter over the ocean. You have to compute the gravity change. We recently did a study with collaborators in China. So she actually used altimeter data, basically the along track gradient, in Japan before and after a volcanic eruption. So we argue that we actually see the signal. So I wonder whether that's what the person who make the question is talking about. And for Grace, actually you could see a very large earthquake, for example, the Sumatra earthquake. So that was actually first published by using Grace data in 2006. By the way, I saw a question that how do you access the Grace data? They are all free. Actually, all you need to do is to search for Grace data online on Google or any Yahoo. You'll find the data product. Actually, they have visualization data product where you could actually get the very high level data in the world, and you could point to a region, and then they will send you the solution, and then you could download the data. So they call it MassCon solutions. So there are many solutions, and they are tools as well. So if you have questions, you could actually ask me also. I have the email address.
Sure. Maybe Dr. Nurul can ask something about the experience on SAR deformation study related to the earthquake. Dr. Nurul?
Thank you. It's just that probably there's nothing much that I can share, but I just wanted to share that there are one students from ITS in Surabaya coming to UTM last year for her she was in the beginning of a master studies where she conducted the land deformation studies, but she didn't really use the altimetry, but instead she used the SAR interferometry to see to see this land deformation in Surabaya. Yeah.
All right then. Thank you for the response, Professor Shum and Dr. Nurul. We have another question here in YouTube channel. One of the participants here asking about his Rizky Dimas Permana from the Sumatran Technological Institute. So ITERA, we call it here, Institute Teknologi Sumatera. He has two questions here. The first one is what's the difference between the coastal altimetry product and a sea level product from marine Copernicus, the product from Europe, right, from the EU. So maybe this question goes to both of you, Dr. Nurul and Professor Shum. And the second question is, he has done a validation of the two products, and the result is that the marine Copernicus product has higher accuracy against the type gauge in situ data. So if Rizky wants to make the questions more clear, you can unmute yourself and then talk directly to Dr. Nurul and Professor Shum. Otherwise, they can just directly answer the questions. Is Rizky there? Oh, it's on YouTube. I'm sorry. So she cannot answer my question in Zoom. So you can just respond to Professor Shum.
I think that the first question is he is asking about what is the difference between the coastal product and the marine data in the Copernicus,
Yes.
if I'm not mistaken. So as far as I know, the coastal altimetry products that I've shown before is from the Aviso website. And meanwhile, and in the Aviso, the coastal data product that's available is from the JSON from the conventional altimetry, like from the JSON, Pistache, and PPIIG product. But for the marine Copernicus, that was where I download my SAR altimetry data, which is the Sentinel-3A and Sentinel-3B. So these are two different websites, and through the marine, the Copernicus, that one is on the GPOT, European Space Agencies. And you can get access to their what so-called like open online sources, where you can also conduct basic data processing in that platform. I hope that answer your question, Rizky.
Yes, and the second question, Dr. Nurul, if you can answer.
What is actually second question, Pak Budi, Dr. Budi? I don't really get the question actually.
Okay, I can repeat it again. So Rizky mentioned that he has done the validation of the two products, and the result is the marine Copernicus product has high accuracy against the tight gauge in situ data. So maybe you can have a comment on this phenomenon.
Well, yeah, that is actually what we are expecting from the, as I said, that we have this low resolution mode of altimetry, and another one is the SAR altimetry. So on the Copernicus is basic from the SAR altimetry, which is Sentinel-3A and 3B. And we are expecting better performance of the data from the SAR altimetry instead of the coaster product from the low resolution modes. So I think that the results, it sounds reasonable and logical, and it is actually what we might expect.
All right, so it's quite clear from Dr. Nurul's explanation. Professor Shum, you have another extra explanation for those questions?
Can you repeat the question? Is it the?
Yeah.
I didn't quite catch the question. Sorry.
All right. Someone has done the validations of the two products, and the results is that the marine Copernicus product has high accuracy against the tight gauge in situ data.
Well, actually, I don't know exactly how to comment. So basically, the question is whether in the ocean, in the coastal ocean, whether satellite altimetry should be more accurate than in situ data. Is that the sort of the question?
Yeah, probably it's already been answered by Dr. Nurul as well. That is already expected like that. All right, so can we move on to the next question? There is this is my colleague Rustam. He's asking to Professor Shum if we have any experience on the modeling of the wildlife habitat by SAR remote sensing or something.
So that's a very good question. I haven't done that before, but I could imagine that if a certain wildlife correlated with water level, or actually maybe the I don't know, the density of the mangrove forest or in the wetlands, then you could somehow so basically wildlife probably would prefer water. If it's dry, then wildlife would move somewhere else. So that's the only thing I could relate to. So I don't know whether I answer your question. So basically, using this geodetic data or maybe imagery data, you could find out where are the water in a wetland and how do the water change. You could sort of correlate to where the wildlife is, and the duck probably would go away if there's no water, meaning there's no food, right?
All right, thank you very much, Professor Shum. We move on to the next question. Actually, Rustam is one of my close colleagues in the field that we usually do the research together. So this is a good progress for us to collaborate more. So another question comes from Bing. He or she is asking about what's the current applications of the satellite altimetry in marine geohazards? Probably in terms of predicting the marine landslides or something related to that. Do you have any comments on this, Dr. Nurul or Professor Shum?
So marine landslide, do you mean undersea landslide? You know, like volcanic, earthquake, seismic landslide?
Yes.
Okay. Satellite altimetry is probably would be very difficult to measure undersea sediment change. I think that's what you meant, right? However, if the submarine like volcanic eruption is big, you could actually measure sort of gravity, but that's quite difficult to measure. And whether you could use gravity, and gravity, you mean Grace data, it doesn't have the resolution to do that. So the method I mentioned. So by the way, why altimeter measures the ocean surface can actually measure the gravity or the bathymetry. So this is the so-called accidental science. When people, when previously launched satellite altimeter, they were thinking about measuring the marine gravity, but scientists like David Samuel, Walter Smith, Annie Kosanoff, they actually thought about do a very classical technology in geodesy, which is basically downward continue to sea floor and then invert for the changes, because altimeter, the sea level actually responds to whether you have a mountain in the ocean or a valley in the ocean. You could see a dip if there's a trench in the ocean. So by that logic, you could actually measure the gravity. So when you talk about hazards, so this is change of gravity is even harder to measure. Just like Grace is more, Grace could measure the signals. That's more difficult to measure by using a regular sensor. I don't know whether I answer your question. So there are many applications people cannot think of, or it's not originally designed. For example, altimetry or GPS for that matter, right? So you could, a lot of times you have a science or application. A lot of times you could figure out a very ingenious way of processing data and pull out the signal.
Thank you for the explanation, Dr. Shum. Just out of curiosity, what's the resolution of bathymetry that we could get from?
Bathymetry. Okay, yeah. So this is so right now you look at the altimeter trace. So that would be the resolution you go for. But every satellite, almost every satellite altimeter before they die, now all the space agencies making it to be non-repeat. But still, I do not think that it's going to be better than, like, I believe 20 kilometers or maybe 10 kilometers. David Samuel has a paper. I think he put it at about 10 or 15 kilometers cross track. So the next altimeter, the wide swath, that's going to give you a very high resolution. But again, the bathymetry, you could only invert for the high frequency. So in other words, the low frequency you're not sensitive to.
I see. Right.
High frequency meaning, you know, mountain ridges and so on. But there's a problem in the coastal region because altimeter is less accurate and it's covered by sediments. So you can actually measure the geological structure underneath the sediment, but the seafloor is really covered by all these sediment, soil, and so on.
Thank you, Professor Shum. Dr. Nurul, you have any words to add?
Well, I think that is a clear explanation from Professor Shum, but it's just that probably we look at the climate change impact, where we can usually monitor the sea level rise using the satellite altimetry. This is a very good tools where we can have, because we already have about 30 to 35 years long terms of data time series. Then we can actually get a very good estimation of this about the sea level rise, and usually this can be related to the coastals managements, to monitor these coastal geohazards. For examples, like we look at the impact to the coastal erosions, coastal inundations, and flooding. Yeah.
All right, thank you very much, Professor Shum and Dr. Nurul. I see one last question from Dr. Johnson Lumbangao. You mentioned using CAWRES in Southeast Asia, resulting the RMSE of 5 to 18 centimeters. From your opinion, how is the strategy to decrease the error in this area? Maybe it is specifically to Dr. Nurul, right?
All right, thank you, Dr. Johnson. All right, so this is about Chorus, the expert system that we developed with back in Newcastle University with Professor Dr. Zhao Li Deng. And actually, at this stage, we are still trying to improve the performance of the Chorus, and we actually now working on Chorus 2.0, in which in this Chorus 2.0, we're trying to improve that RMS error to get a better estimation, particularly in terms of the offset reduction. You know, we embed that neural network techniques. So we're trying to conduct more assessments to understand the behavior of the offset. We now have so many retracking algorithms, coastal algorithms. So we put so much efforts to see how these offsets values varies. And also in terms because we also saw another factors that affecting the accuracy is the variations of the significant wave height. So yeah, we are working on Chorus 2.0, and hopefully we can come up with a new paper in journal paper next year. It is halfway to go through on the simulation results.
All right, continuing that question, there's another question from Bing. It's asking about is there any plan to incorporate more retracker into the Saurus system? And what's the biggest challenge faced when developing the algorithm?
Yeah, incorporating more retrackers, it doesn't mean that we would like to incorporate all of the coastal retrackers that we have, because we got so many new coastal retrackers these days. But one interesting findings that we found when we conducted this retracking performance over the Southeast Asia is that we found the ICE retrackers is performing much better than the physical retrackers of the MLE4 when we compare that with the tide gauge data. So ICE retrackers is actually meant for the inland water, but it has been widely used also to the coastal. And yeah, in Chorus, we try to embed the existing ICE1 retrackers from the standard product into the Chorus system. But others like ALES or other retrackers, we do not have a plan to add it because it is going to make it, the system becomes getting more complicated and takes a longer time to reprocess our data. So the strategy is that to analyze how good is how significant is the performance of a retracker, and then we if it is excellent, then we'll bring it into the chorus system.
Thank you very much, Dr. Nurul. So I see no more questions. So if you don't mind, can I ask a question to Professor Shum or Dr. Nurul at once?
Sure.
Okay, let me share my screen a little bit, just 2 minutes or something. So hopefully you can see my screen already. So in the screen, you can see some part of the East Kalimantan or East Borneo that has some peak region. So with the dark green color there, this is the image from Sentinel-2 imagery. These are some peaks that we have in East Kalimantan. So we have a lot of interest to do the research in this area. And the question is, do you think, maybe from to Professor Shum first, because the area is quite small. So from the most left point to the most right, like from the west to east, it's just about 20 kilometers in extent, in the length or in the width. So do you think race information can still help us to identify how much or how deep is the pit in this area? If the length or width is just 20 kilometers.
Yeah, can you tell me what is the red again? Are these features?
The red features are the open area, and usually it's coming from the oil palm plantation that's still doing land clearing. So they are clearing up the vegetations, and they are now going to plant it with the oil palm.
Yeah.
But then the dark green are the remaining pits in this area, and we actually have a lot more in North Kalimantan and even more in West and Central Kalimantan with the wider extent. So how do you think about using the trace to detect this?
Right. Yeah, Grace has these 600 kilometer pixel, right? Versus your Sentinel-2 is how 5 meters, 10 meters? Is that
10 meters, Professor Shum?
10 meters, okay. Yeah, so this is very different scale. However, I know that you're studying forestry, right? I believe, let's see, there was a paper using graves to detect forest fire in Indonesia, I believe. So forest fire, although at a very big scale, but Indonesia has a huge forest, right? Or Amazon is larger, but Indonesia is also. So graves actually could detect what is dry and what's not dry. And my understanding of some of the forest fire is that some forest fire could start burning and you cannot see it. I forgot the terminology, and you are an expert. So sometimes it started burning and nobody knows until it's too late. At a very large scale, graves potentially you could actually sense the dryness. Basically, you're losing. So the factors triggering a fire, of course, is temperature, and then lack of water, right? Dry soil moisture. So this is exactly what graves could see, what could sense underneath the very thick forest, because your optical imageries, your whatever, even radar, you can't really see the bottom, but graves could. So maybe think about that. However, I guess it's very cost scale. There's a way of down scaling the graves signal. However, the most you could probably do with a believable will be 25 kilometers or maybe 100 kilometers. But it is definitely a tool that people are talking about. In other words, sensing like hidden forest fire is very thick. You can't see it, but somehow, or like you could use it to predict forest fire using some index, right? So to me, that's a very legitimate tool. And
thank you.
There's one kind of satellite data you may be able to get it for free. I don't know. It's called Planet Inc.
Yeah,
It's like supposedly a 3 to 5 meter type of resolution. But the significant thing is that they argue they have daily sample. So we've done some research on fire and on other hazards like flood. Some of the data is actually like a daily sampling. It's very impressive.
Okay, thank you very much for the response, Professor Shum. Is there any of the participants who want to ask a question directly to our speakers? And don't forget, we also have Pak Hafiidh from S.Si. Can answer your questions related to any matter related to geospatial information. Anyone? Yeah. Okay. Then I saw a lot of participants here coming out from East Kalimantan, even from some coming from Malaysia, I guess. There are some people also coming from other provinces, but most of the participants right now are coming from Mulawarman University. So at the end of this talk, at this webinar, I will kindly ask Pak Anton or Ibu Unis as the head and the secretary of the Institute of Research and Community Services of Mulawarman University to kindly provide us with the closing remarks and closing ceremony if you are still in this meeting. Pak Anton or Bu Unis, are you monitor? Okay, seeing none, then I'll, I'll dare myself to conclude our webinar today, which is very, very informative and comprehensive. One big message from our rector is that we have to increase our collaborations in research and also in community service. But in this case, probably we will do more on the research collaborations with Dr. Nurul and Professor Shum in the future in many kinds of schemes. So we have the schemes of visiting scientists, we have the scheme of postdoctoral research, we have the schemes of collaborative research with the mutual fundings from both sides. So hopefully in the future we can talk about it in a very much detail to involve many more scientists from Mulawarman University. Also, we thank you very much for Mr. Hafiidh from S.Si Indonesia, who give us a very good sense on how geospatial information is used by coastal and marine applications. And by saying thank you to our great and almighty God, we are closing this webinar with very good appreciations to the speakers, Professor Shum, Dr. Nurul, and Pak Hafiidh, and also, of course, to all of our participants today. So here I'm closing the webinar, and feel free to greet each other and open up your mic to say hello to other scientists. Thank you very much and have a good day. Stay healthy, stay clean, and keep away from COVID-19.
Thank you very much, Pak Budi.
Thank you very much, Dr. Nurul, Pak Budi.
Terima kasih Pak Budi.
Most welcome, Bu Nurul, Pak Johnson, Pak Hafiidh, Professor Shum, and everyone.
Thank you very much. We had fish yesterday for dinner.